So let's go ahead and talk about what a titration is. A titration is where you take an unknown concentration of either an acid or a base and you add a known concentration of an acid or a base to neutralize the solution so that you can determine how concentrated the unknown solution was. So if we're given an unknown acid, we would neutralize it with a known base. And if we're given an unknown base, we would neutralize it with a known acid. And so what we're going to do is use this particular chemical reaction to help us learn how this graph works and how we can determine the unknown concentration of an acid. So let's say that we have an unknown concentration of hydrochloric acid, and let's just say that it's right here. Now, I know I put 5 moles there, but we're going to pretend we don't know it's 5 moles for now. Well, what we can do is we can put a known concentration of base within the acid. So again, there's 5 moles of acid inside of this beaker, but we're going to pretend like we don't know that. So let's go ahead and say that we put 1 mole of sodium hydroxide inside of this beaker. Well, when we put 1 mole of sodium hydroxide in this beaker, that 1 mole will react with 1 mole of hydrochloric acid. It's going to neutralize 1 mole of hydrochloric acid because this is a 1-to-1 ratio. And what we will end up with is 4 moles of hydrochloric acid. So again, we put 1 mole of this in solution. It neutralizes 1 mole of hydrochloric acid, and we're left with 4 moles of hydrochloric acid. Now, something that I didn't mention yet is we actually can use what is called an indicator to tell us if something is acidic or basic. And to give you an example, there's a certain indicator called phenolphthalein, and phenolphthalein happens to be pink when it's in an acidic solution, and it happens to be clear, colorless clear, when it's in a basic solution. And so if we have this right here and we put phenolphthalein in there, it'll be pink because it's got an acid in there. And because there's still an acid in there, it'll be pink as well. Now, I think that a question that a lot of people have is, well, what happened to this 1 mole of sodium hydroxide? Isn't it still in there? Well, no, because this 1 mole of sodium hydroxide completely reacted with the hydrochloric acid and it went to product. So there's actually no sodium hydroxide because it completely reacted with that 1 mole of hydrochloric acid. Now, let's go ahead and say that now I'm going to add 3 moles. I'm going to add 3 more moles to this solution just to speed it up a little bit for this example. And if we add 3 moles of sodium hydroxide, we end up with 3 moles, 1 mole of hydrochloric acid left over. So again, these 3 moles will react with 3 of those moles, and 1 mole will be left over. Now, is it going to be pink still? Well, yes, it will still be pink because phenolphthalein is pink when it's in solution. Now, let's go ahead and I'm going to add 1 more mole. Let's go ahead and add 1 more mole to this. And when I add 1 more mole, how many moles are left over? 0 moles of HCl are left over. And if there's 0 moles of HCl, will the phenolphthalein be pink? The answer is no, it will not. It actually will now be colorless. And so this is the point in which we can actually stop adding sodium hydroxide because we've reached the point where there's no more acid. And so how many moles did it take to reach that point? Well, it took a total of 5 moles because all of these added together add up to 5 moles of sodium hydroxide. And because we know that we put 5 moles of sodium hydroxide, and we know it's a 1-to-1 ratio, that's how we can determine that there was originally 5 moles of acid. And again, we're pretending like we did not know that there was 5 moles of acid. But for this example, we, just pretended. But anyways, now at this point, the solution has become colorless. And I want to talk about what type of solution did we have before. Well, we started off with an acidic solution. We started off with and then we ended up with an acidic solution in this after adding the first amount of sodium hydroxide. We still have an acidic solution in this third beaker, again because there's hydrochloric acid in each one of them. But what do we have in this particular beaker? We have a neutral solution. And if you remember, a neutral solution has a pH of 7. Now, what would end up happening if I added some more sodium hydroxide? So let's just say I add, 2 moles of sodium hydroxide. Well, if I add 2 moles of sodium hydroxide, what would I end up with in here? I would end up with 2 moles of sodium hydroxide, because there's 0 acid to react with that sodium hydroxide. So the sodium hydroxide does not react, and we end up with a basic solution now. Now let's go ahead and relate this to the graph. This first situation, before we add any base to it, is going to be this part of the graph. And I'm going to make it blue. So this situation is that first part. But when we add some amount of sodium hydroxide, we are now somewhere in here. And then once we get to this point right here, we're somewhere over here, because again, we're acidic. But then once we get to this point right here, where there's 0 acid left over, what happens is the pH becomes neutral. This right here is where we can stop titration. This is the point at which there's no acid, there's no base, the pH is 7, and that tells us how much acid was originally in there. Now, if we were to continue adding base, what would end up happening is we would end up with this right here. So we can add base, and we can keep adding base, and the solution would just become basic. Now, this particular graph, let's go ahead and take a look at this graph here. This particular graph says that we added 25 milliliters. Says that we added 25 milliliters of sodium hydroxide. And so we can use that information to then figure out what was the original concentration. Let's go ahead and look at an example of a unknown base. So if we have an unknown base, which essentially would be this same exact situation except for backwards, we have an unknown base but we're adding acid to it. You can see that we'll start off as basic, and as we add the acid will be neutralizing some of the base, but the solution will still be basic until we reach the point that there's no more base and there's no excess acid, which is going to be right here. So this is the equivalence point, the point at which it's a pH of 7, and then if we were to continue to add acid in this situation, we would end up with an acidic solution. But in this situation, it took, again, 25 milliliters to reach the equivalence point. So in a titration, the equivalence point was reached when this many milliliters of this concentration of hydrobromic acid was added to 20 milliliters of an unknown solution of lithium hydroxide. Now there's a couple things we need to keep in mind. We need to remember that molarity is moles over liters. And we also need to write a balanced chemical equation. Now, what it's saying is that we do not know the concentration, which again, concentration is molarity. We do not know the molarity of this lithium hydroxide. And to figure out the molarity of it, we need two pieces of information. We need the liters, which it actually gives us right here, and we need the moles, which it does not give us the moles of the lithium hydroxide, but what it does give us, it gives us the molarity of the hydrobromic acid, and it gives us the liters, which I'm going to go ahead and just already convert it to liters. Since we have the molarity and the liters of the hydrobromic acid, we can use the molarity equation to figure out the moles of the hydrobromic acid, which gives us 0.039 moles. Now, this is a 1-to-1 ratio, which means 0.039 moles of this will react with 0.039 moles of this. And now that we have our moles and our liters, we can take our moles and our liters and calculate the molarity, which happens to be that. All right, so let's go ahead and do this next problem. It's the same exact type of problem, except it's now asking for how many liters, what volume of the sulfuric acid would be required to neutralize that. So again, first thing we do is write a balanced chemical equation. And then let's go ahead and look at what's given to us. We have a 0.13 molar solution of this. The question is how many liters of this will be required. It gives us the molarity of this, which is 0.17 molar, and it gives us the liters of this, which is this. Now we can use our molarity equation to figure out how many moles of lithium hydroxide there are. And then what we can do is, since this is a 2-to-1 ratio, we can go from moles of lithium hydroxide to moles of sulfuric acid. And then once we figure out the moles of the sulfuric acid, we also have the molarity, and so we can plug that into our molarity equation to figure out the liters, which gives us 0.018 liters or 18 milliliters. The problem did not specify whether it wants it in liters or milliliters, but I just put that there just because. All right, so this is the same type of problem. It's giving us a certain concentration of hydrochloric acid, and then it's giving us an unknown concentration of lithium hydroxide. So the first thing we need to do is write a balanced chemical equation. And it gives us the concentration of the hydrochloric acid. It also gives us the volume of the lithium hydroxide, which is 0.0500. It's asking for the molarity of the lithium hydroxide, and it actually, in the problem itself, does not give us the liters of the hydrochloric acid, but on this graph, we can actually determine how many liters it took to get to the equivalence point. So go ahead and pause the video real quick, and I want you to try to look at this graph and determine at what point or how many milliliters it took to get to the equivalence point. Well, the equivalence point is right there, which happens to be around 25 milliliters. So it's going to be 0.025 liters. Now what we can do is we can use the molarity equation to figure out the moles of hydrochloric acid, which is going to be 0.014 moles. This is a 1-to-1 ratio. So that means whatever moles of hydrochloric acid we have the same number of moles of lithium hydroxide. And then we can use Again, the molarity equation to take moles divided by liters to give us the molarity. For this next problem, it's a little bit different because it does not give us the concentration of the known acid, but rather it gives us the pH. But again, we can always take pH and we can figure out what the concentration is. But before we do anything, we always have to write a balanced chemical equation. And we end up with this balanced chemical equation. Again, we have 0.0425 liters of the HBr and 0.0250 liters of the NaOH. It's asking for the concentration of this, and it gives us the pH of the hydrobromic acid. Well, the molarity or the concentration of the hydrogen ion is equal to 10 to the negative pH. And so if we use this equation here, we can actually calculate the concentration or the molarity of this particular acid. So now that we have the molarity, which is 0.034, we can use the molarity equation to figure out the moles of acid. Now this happens to be a 1-to-1 ratio again, so it's a 1-to-1 ratio, which means that however many moles of HBr there are, it will be the same number of moles of the NaOH. And then again, we can use our moles over liters give us molarity equation to solve for molarity. And our answer is 0.060 molar solution. So let's go ahead and talk about this particular problem here. I already did part A. Part A is exactly like the other problems. So go ahead and pause the video. Try to solve for part A here. Keep in mind that this is a 2-to-1 ratio. And once you're done trying to figure out and get the correct answer here, then resume the video. Now for part B, we need to sketch a graph of the curve. And to do that, it doesn't need to be perfect, but there's a couple points that we want to, there's really 3 points that we want to do. We want to know what the initial concentration is. We want to determine 2 different points. We want to determine the initial pH, and we want to determine the equivalence point. The equivalence point is actually the easier one to do, so let's go ahead and do that. The equivalence point is the point at which the acid or base is neutralized. So it's going to occur somewhere at a pH of 7, and it tells us right here that it took 45 milliliters to get to that point to where it's neutralized. And 45 is probably around there. So our equivalence point is probably right there. Now, the other thing we want to talk about is the initial pH. Now, what is the initial pH of the unknown? Well, the unknown is the calcium hydroxide, which is a base. So we know that it's going to be a basic solution. So that means the curve is going to start up here somewhere. Now, the known concentration that we have is that of the acid. And as we proceed with the curve, we're going to end up somewhere down here. So to find the initial pH, we know the molarity of the solution, of the initial solution, so we can actually determine the initial pH by taking the negative log of the concentration to figure out the initial pH, which gives us 0.26. Now, what I will say is you do not need to graph this perfectly. So the initial pH is 0.26. And actually, I misspoke. This is the original pH is not 0.26. This is the pOH, and again, pH plus pOH is what gives us or adds up to 14. So we can use this equation to figure out what the original pH is, which actually gives us a initial pH of 13, around 13.7, somewhere around there. Now again, it doesn't have to be exact, it's just that it's somewhere up here. So we know that we're starting somewhere up here. Now again, we're sketching the curve here, and we're just estimating what it is. So again, as we add acid to this initial base concentration, the solution becomes less basic until it gets to the point here where there's no more base, and we reach the equivalence point. Now this is the point in which the problem actually stops. It doesn't go beyond this point, but we're going to take it beyond this point, because if we were to continue to add acid, it eventually would become acidic. So again, the problem is actually just telling us this part. It gets to here, and then after that, as you add acid, it becomes more acidic. And so this is the sketch of the curve, and I'm going to go ahead and take these parts off because we don't need them, but essentially it looks like that.